Greetings, Earthlings. This Art of Math series is meant to be so much more than just preparation for an exam. If that's all you're using it for, you're probably getting only like 5 to 10% of the benefit. That said, I want to show you guys that these videos can very quickly help you in a lot of contexts on a lot of exams. MATHCOUNTS, AMC, SHSAT, SAT, ACT, TASC, whatever your favorite exam is. Please note that there are a lot of topics that I haven't yet covered, such as geometry, probability, and other things, but there will be plenty of future videos covering way more topics, so I'll limit this application video to just the existing videos, roughly the first 70. In this video, we'll go over 10 to 11 math counts problems to show you how certain existing videos from this series apply to these problems. I'll link them in the video and description for your convenience. But I could just as easily have picked questions from the other exams. So, for example, if you don't really care about this and you just want to know about the SAT, hang in there. It's going to help with that as well. Okay, as many of you already know, success on these exams involves knowing the content, but also speed. Now, there are 3 things you can do to improve your speed. Refine your technique, practice lots of problems, and cultivate the habit of looking for alternate and elegant solutions. So this series is really going to help with knowing the content, refining the technique, and cultivating this habit. Practicing lots of problems, that's something you guys should be doing in addition, seeking out other videos, other textbooks, school, whatever it is. That this is something that this series won't hit 100%. Okay. The bottom line is that whether you care about math counts, the SAT, another exam, or no exam, this series will help on all fronts. So if you're just joining us with a specific goal in mind, I encourage you to use this series in order for that specific goal, but also to keep an open mind, because that way you may get more out of the series than you even hoped or imagined. So you may want to follow it in order, maybe skip a few things if you're in an emergency situation, but try to follow basically in order. Okay. Finally, if you have any questions, comments, anything at all, as usual, I would love to hear from you guys. Please post your comments and subscribe to stay up to date. If you have questions about specific exams, feel free to ask questions, comment about that as well. Okay, here we go. So, just so you guys know, for the rest of these are going to go from 1 through 10. These are just going to be 10 questions, and all of them over here we'll have the original math counts problem. So this is math counts 2016 school competition, the sprint round number 9. And over here the arrow will point to the Art of Math, which is this series. Which video is the relevant video? So you want to look at this number, which is number 16. So if you feel like, hey, I want to learn more about what we just did in this video, you're going to go to number 16 in the series, which will be about habits and counting. All right, here we go. A length of 240 feet of fencing is to be supported by a total of 13 evenly spaced fence posts, including 1 at each end, as shown. How far apart must the fence posts be spaced? So, as long as you don't do 240 divided by 13, which is the knee-jerk reaction, you're going to be fine. So you have to realize if there's 13 fence posts, there's only 12 spaces in between those 13. So you want to divide 240 by 12. So to practice that and get a little better feel for that, you're going to want to go to this video. All right, that's all I have to say on number 1. So make sure you're not dividing by 13, but by 12. All right, this one's kind of an interesting problem. How many triangles are in the figure shown here? So again, here's the original question, and here's the video you should go to learn more about it, number 18. So there's several approaches. How do we count the number of triangles here? The key point is you want to stay organized. So what you don't want to do is just start saying, oh, I found one, 1, 2, 3, 4, and lose track of it. So you could focus on many things. You can focus on the small ones. So, for example, size, count them by size. You can say, hey, how many involve this point? So you could focus on point, and you could focus on a lot of other things. So there's many ways to do this. We're going to focus on size, and I propose that's going to be a good organizational scheme. So for example, size, you may have, let's focus on this triangle right here. So we'll call this side short and short, So we'll say 1 short by 1 short. So how many of these are there? There's 1, 2, 3, and going around there's going to be 3 per side. So there's going to be 12 of those. Then you could say, oh, well, how about what if I have, instead of 1 by 1, I can have 2 by 2. So like this triangle over here. And there's 1, 2 per side. And if you flip it, there's 3, 4, 5, 6, 7, 8. So there's 2s by 2s. So like two of these short sides by 2 of these short sides, there's 8 of those. Then you can say, what about if it's this huge triangle, which is 1, 2, 3 right here? So there's 1 of those per side, and each of the sides will have 1. So 3s by 3s is another 4. Now at this point we're up to 24, but we've missed some. So what if you have 1 medium by 1 medium? So a medium would be, let's say, this triangle right here, because this side is a little longer than this side. So that's why I'll refer to it as a medium by medium. So each of the corners will have 1 of those. So that's going to be 4 of those. But you could have it be 2 mediums by 2 mediums. So that's another 4. Or you could have 3 mediums, which would be this huge half of the square. And there will be 4 of those. So it would be 1, 2, and then the other diagonal. So 3 mediums by 3 mediums, that's another 4. So what do we have? That's 20, 24, 28, 32, 36. So hopefully you should get a grand total of 36. The point is, though, is not how to do this, but if you picked a bad organizational scheme, which is just random or size or point, you're going to have a lot of trouble doing this. So I refer to you guys to number 18 to go over problems such as these. All right, next one. J.R.R. Tolkien, author of The Hobbit, stated in 1970 that on one of his birthdays, the age he turned was the square root of the year. In what year was he born? So let's say we could find this special year, which is the age he turned when he was the square root of the year. So if we could find that birthday, then from there we should be pretty good. Just know you're going to have to actually subtract a little bit to find the year he was born. So how do you do that? That's the square root estimation video, number 14. We might want to poke around. Let's try 40 squared, 1600, 50 squared, 2500. All right, so we're kind of close to 1970. So as soon as we get something really close, then we can zero in. So you might try 45 squared, and using a trick, that's going to be one of the mental math tricks in the series as well. That's 20, 25. All right, so that's pretty close. So maybe you want to try 44 squared, 43 squared, and we'll very quickly zero in. I'll leave the rest for you guys to do, but in general, how do you do this fairly rapidly? Go to number 14. All right. Kelly has $12 in dimes and quarters. She has 6 more quarters than dimes. How many dimes does Kelly have? So there's 2 ways to do this problem. There's the regular solution in the series number 57, and there's the cool solution, which is 58. So most of you guys, if you've learned systems of equations, you'll probably know how to solve this using the approach that you could find in video number 57. And that'll be saying, for example, I have some number of dimes. This is the number of dimes. There's Q, which is the number of quarters. And we could set up some equations. So we have, she has 6 more quarters than dimes. So quarters is dimes plus 6. So that's your first equation. And then you can come up with this $12 equation, which is Q times 25 cents plus dimes times 0.10, and there's your second equation. Now you could solve it this way, and that's what this video will go over, but there's a cooler way. So I'm not going to go over the cool way in this video, but it basically involves just guess what you think is the answer and then tweak it a little bit, and that's going to be much faster. So check that video out. All right, this one. How many ordered pairs of integers a and b satisfy a times b is 60? So 60 is 4 times 15, or 2 squared times 3 times 5. Now from here, using what we go over in number 24, you can add 1 to each of these powers. so that 2 becomes a 3, the 1 becomes a 2, the 1 becomes a 2, and then you just multiply these. So that's 3 times 2 is 6, times 2 is 12. So that means there's 12 factors. That's how you find the number of factors of 60. So you might say, okay, so since there's 12 factors, there should be 12 answers. But don't forget they're integers, so you have negative numbers. You're going to have to double that 12. You could have also just listed 1 and 60, 2 and 30, 3 and 20. You can keep listing this, but check this video out for how to understand and do this procedure. All right. So if 3 Zoguts and 4 Gamoons together cost $18, and 2 Zoguts and 3 Gamoons together cost $13, what is the combined cost of 1 Zogut and 1 Gamoon? Now, if I'm pronouncing these, I'm sorry to all the Zoguts and Gamoons, or Zoguts. Okay, check out number 55. And by the way, for a lot of these, you may want to go to this video and also look a few videos before and a few videos after, so that you can learn this a little better, because there's additional stuff. So you may think like, hey, 55 didn't completely cover it, or so that's just like a reference point. Start there and maybe go 1 or 2 back, 1 or 2 forward. All right, so 3 Zoguts, that's 3 Z's and 4 G's. Now here we have 2 Z's and 3 G's. Now using combination of systems of equations, we say, hey, let's subtract these. If we subtract these, we'll have 1 Z and 1 G. So rather than solving this complicated system of equations using our whole rigmarole procedure, let's just subtract these. And what that tells us is we get exactly what we want, 1 Z and 1 G. So that means all we have to do for this problem is subtract 18 minus 13 and you're done. That's it. All right, part B. 2 numbers have a sum of 1,000 and a difference of 2. Exactly one of these numbers is prime. What is the composite number? So there's 2 ways to do this. One is to actually set up the system of equations, which is x plus y is 1,000 and x minus y is 2. We won't bother doing that. Given the numbers, a lot of you will probably immediately see, hey, 501 and 499 are 2 apart and sum to 1,000, so you don't need to solve the system. But if you want to go into that, that's number 55. And now we're going to use video number 20, which is divisibility rules, and see, hey, which one of these is the prime number? Is it 499 or 501? Well, 501, using the 3 rule, you could see is divisible by 3 because the sum of the digits is 6. So that's the composite number, and therefore, since they told us exactly one of these is prime, this must be the prime one, so 501 is the number you're looking for. All right, next problem. What is the greatest multiple of 3 that can be formed using one or more of the digits 2, 4, 5, and 8, assuming no digit is used more than once? This is a cool problem if you've never seen it before. So we're going to approach this pretty cleverly. So all we're going to need is video number 20, which is the divisibility rule for 3. So let's add up all of these digits. Like let's say we have 2, 4, 5, 8, which is 2,458. The sum of these digits, that's 2 plus 4 is 6, 6 plus 5 is 11, 11 plus 8 is 19. So if we add these, we get 19. Now 19 is not divisible by 3. So what that means is no matter how you try rearranging these digits, like 5, 2, 4, 8, it's still not going to be divisible by 3. So that means we have to kill off one of the digits. Now we want the greatest, so we don't want to kill off our greatest digit, we want to kill off the smallest thing possible. So let's try killing off the 2. 5 plus 4 plus 8, that's 9, plus 8 is 17. Still no good, because 17 is not divisible by 2. So instead of the 2, let's try killing off the 4. So 5 plus 2 is 7, 7 plus 8 is 15, very good. So that's divisible by 3. Now we just want the greatest number, so let's start off with the highest digit, 8, then 5, and then 2. So that's how you do these problems. You don't want to just poke around, that'll take too much time. All right, next problem. 2 squared times 4 to the 4th equals 2 to the k, where k is some mystery number. What is the value of k? So you want to look at number 29 exponents and number 30 factoring. Although that involves a plus instead of a times, it's very similar. So bottom line is, these are not all 2's, so we're going to make them all 2's. That 4 is related, so we're going to make that 4 a 2. So we have 2 squared times, what's a 4 in terms of 2's and exponents? 2 squared. And we keep that original 4. 2 to the k. All right, now we just use our exponent rules. So a power to a power is, you multiply the powers, that's 2 to the 8th. And to see why that works and all this stuff, again, go to these videos. 2 to the k. All right, we add the 2 and the 8, and we get 2 to the 10th is 2 to the k. So the key step is realizing we want to break this 4 down to have it all be 2's. So, and from here we can see the k is 10. All right, next problem. If a, b, and c are integers such that a plus b over 2 is 3, b plus c over 2 is 4, and a plus c over 2 is 5, what is the value of a plus b plus c? So first thing, let's get rid of these ugly over 2's. We don't like those. So let's just say a plus b is 6 from here. B plus c is 8. And a plus c is 10. What is the value of a plus b plus c? So using the same thing we're going to do in video number 71, which is one of my favorite things, tricky algebra, symmetric equations. These are symmetric. To see what I mean, go to that video. We're going to add everything up. We have 2 a's, 2 b's, 2 c's. That's 14, 24. So if 2 of everything is 24, then I'll leave you guys to finish off what is 1 of everything. Right? We would divide that by whatever, you know what it is. The integers 1 through 66 are arranged in 5 columns, A to E as shown, where column C contains the multiples of 3. What is the sum of the numbers in column D? All right, so these numbers are arranged in this wacky way: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and onwards. So we want to find only the stuff in column D. So we have 5, 11, well, we're not really sure what's going on. So let's do a little more. So we have 10, 11, 12, 13, 14, 15, and then going this way we'll have 16, 17, 18. The reason I wanted to do a little more is to see this pattern. This tells us that it's 5, 11, 17. That's plus 6, plus 6. That's great. I mean, this is going to keep going and adding 6. So the next one will be 23 and onward. So the only question now is, where do we stop? They said we're going up to 66. So since all of these are multiples of 3's, 66 will be in the middle. So now the question becomes, are we going this way to hit a 66, or are we going that way to hit a 66? So to do that, we're going to look at these. The multiples of 6 are every other line, and they go from right to left. So that means this is going to be 64, 65, 66 going this way. So that's very good for us. That means we know where we have to stop, which is here. So we're going to be going 5 plus 11 plus 17 plus blah, 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 dot, 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 all the way up to here. Now, how do you add that up without actually manually adding everything? Go to video number 37 on special sums. All right. And so that's all, folks. I'll see you guys in the next tricky algebra video. And if you're just joining us, I recommend you start from the beginning of the series with the introduction and follow along the playlist in order. See you guys.